point, we've examined samples where we know what the population standard deviation is for that particular population, samples from that population. Um, we've learned that we can compare that result to something that we believe might be the true population standard deviation. I have a simple example of that right here. This is not exactly public. I guess it is public health, I guess, right? A lot of people eat meat, so this might be public health. A herd of 1,500 steer were fed a special high protein grain for a month. A random sample of 29 were weighed and had gained an average of 6.7 pounds. Standard deviation we know for a fact, standard deviation of the weight gain for the entire herd was 7.1. We normally would not know that, right? If we only sampled 29 to figure out their weight gain, we wouldn't normally really in real life know that the standard deviation of the entire herd is 7.1. We'd probably have to estimate the standard deviation of the weight increase based on that same sample of 29 steer. I'm sorry. What did I do?
Did you minimize the go-to meeting?
Oh yeah, let me get that out of the way. Yes, I am. Thank you for reminding me. Oops, I don't want to do that. No, I want to do this. Good. Okay, there we are. That's out of the way now. Okay, so we normally wouldn't know what that standard deviation is for the entire population. But knowing that standard deviation represents the entire population allows me to use the Z table instead of using the T table, right? Because we have a better, if we knew that standard deviation for the entire population, it's one less level of, one less element of uncertainty that we have. So we can use that Z table, which is less conservative than the T table is. T table, all our confidence intervals are going to be wider. All our like our distribution of all the possible samples from this population would have been spread out wider than it would be for the if we knew a standard deviation. We're using the Z table. An equivalent standard deviation for a number of standard deviations apart, 95% of the population would be instead of 1.96 standard deviations to the left and to the right, it might be 2.04 or 2.221, depending on what the sample size is. Okay, that we base the standard deviation on. Okay, so that's a kind of a long-winded discussion of why it's always nice, if possible, to know the population standard deviation. But in reality, that's very rarely the case. But for this example, we're going to say we do. So that means we can use the Z table instead of using the T table. Okay, but we're going to repeat this example, take that assumption away, and we're going to repeat this example, which is going to force us to use the T table instead. So we're going to see a difference in how this works. Okay, so okay, let's read this again. 1,500 steer is fed a special grain diet. That's our population. A sample of 29 were weighed from this population of 1,500 and had gained an average of 6.7 pounds. If the standard deviation of the weight gain for the entire herd was 7.1, test the hypothesis that the average weight gain per steer for the month was more than 5 pounds, was 5 pounds. I'm going to just say was different. Was different than 5 pounds. Okay, so what we're saying here basically is we want to know whether or not we would have expected the herd to, over that period of time, to have gained 5 pounds, right? That's basically what we're testing. Normally that herd in that number of days would have gained 5 pounds. Now with this new feed that these 29 steer were fed, they gained 7.1 pounds. Okay, now the only problem is that when we take 29 steer out of this group of 1,500, we're taking a sample. Anytime we take a sample, there is going to be some risk that the mean of that sample is going to be different than the mean of the actual population, the 1,500. That maybe they didn't really gain 7.1 pounds. Maybe they only gained 4 pounds, right? Less than we would have expected them to weigh. Maybe they would have gained 10 pounds, even more. They would have even greater weight gain than we would have expected. Okay, so what we're going to do now is we're going to say to ourselves, okay, let's set up a hypothesis here. Okay, and what are the rules for the hypothesis? You guys remember what we were talking about? What was the procedure, the 5 steps? Yeah, before I even do that, did we talk about it in the lecture? Did we talk about any of the assumptions that are involved here? What's that? Well, no, I mean, in terms of assumptions about our sample, right? So first, great, terrific, thank you. One assumption is that it's a random sample, right? The other assumption is that the results are normally that the population results are values are approximately normally distributed, right? And I'll just start with those two. Okay, it's a numeric variable, and that they're approximately normally distributed. Okay, so now I can't get this going. Hey, whoops. Okay, so our average for our sample, X bar, is equal to what? Is equal to 6.7 pounds, right? Now, our assumption is that this entire herd, over the period of this amount of time, would have gained an average of how much? 5 pounds, right? Okay, so now we're interested in knowing, what's the probability that we would get this result if there was really an increase in that we would get this result by chance, right? If there was really no difference between using the previous feed and using the new feed on these cattle, right? So what we're going to test here now is we're going to test to see, if these two results are really the same. In other words, our null hypothesis. What kind of test is this? Is this a single sample test or a 2 sample test? Single, there's only 1 sample involved, right? If we had had 2 herds and we fed them different stuff and took a sample of 29 from this herd and a sample size of 35 from the other herd and got 2 different means and we're going to compare the means, that would be a 2 sample test. We're holding off on that until next week. Okay? So what's our null hypothesis here? What's ground zero here? What do we expect the mean to be here? The mean, right, is equal to, what do we expect the mean to be here? 5. Okay, and our result was 6.7. So we want to know what the probability is that we would get that high a value if, by chance, if there were no difference between our sample mean, the population our sample mean represented, and the population that we're comparing it to. Okay, so now how am I going to do that? How am I going to determine what the probability of getting that extreme a value is? Well, we're going to take a look at our normal distribution. Right, here's our normal distribution. Right, our expectation was that the mean was going to be 5.0. What was the mean for our sample? 6.7. Okay, that's way up here. Okay, so now remember, this is a sample. What was the sample size again? It's up here somewhere. 29. Sample size 29. So what's the probability that if the mean is really 5.0, right, that we would get a result as high as 6.7? Okay, well, any result, if I took repeated samples from a population, large population, that had a standard deviation of 7.1, and that if I repeatedly took samples of size 29, I could draw a distribution which would represent what my expectation is for the distribution of all those sample means, right? Since we know, since sigma is equal to 7.1, we know the population standard deviation, right? This distribution is represented by what table? The z table, okay? So I can use the z table to figure out how likely is it that if my population mean is really 6.7, that what's the probability that I would have gotten this big a difference in results?
I'm sorry,
Yes.
I
Yeah.
know you already said this, but with an N of 29, why are we using a Z table?
Well, we're using the z table because we know the population standard
Oh,
deviation.
that's right. Okay.
Okay, if we didn't, we're going to repeat this without knowing that. I'm glad you brought that up because we're going to repeat this again right after this, so that we can see what the impact is of not knowing the actual population standard deviation. Okay, so I know that 95% of the possible sample results I would get for this population, right, is going to be between 1.9 standard deviations below the mean and 1.96 standard deviations above the mean. Now, is 6.7 within that range? Let's figure that out. X bar minus mu over what? Standard error, right? Because these are repeated samples of size 29. So what is standard error here? It's equal to, right, 7.1 over the square root of 29. Okay, first thing we're going to do is figure that out. Whoops. That's something. This is not letting me do that. Somehow or other, I'm locked out here. I can't do that. Maybe I can use. Okay, equals. I'll do it this way. Equals 7.1 divided by square root, parentheses, 29. I won't have the intermediaries, but I'll get the result, which is 1.3. Now, in homework number 4, you'll find that if you round this up too much, if you round this too much to like say 1.3 or something like that, one of the answers is going to come out wrong. At least one of the answers is going to come out wrong. Because as you progress through your calculations, things will happen to increase the error that you introduce by rounding. When I took this course many, many years ago, the professor insisted we were using calculators, handheld calculators. This was at Hunterville. He used to work across the street at, I don't know what that was. There's a dental college or something like that. He used to work across the street, and he was a statistician, and he insisted that you use every digit on that calculator, whatever it was, 8 digits, 8 decimal places or something like that. And you do that all the way through the calculations. We used to do all this by hand and on paper for exams and for homeworks. And he insisted we show all 8 digits, until we got to the very end, and at the very end we were allowed to round the number. So for the homework 4, you're basically going to be using the T table, mostly the Z table or T table. So that will give you, I think, 3 decimal places or something like that. So you should use them all until you get to the very end. Okay, now you understand why I'm saying that like you multiply your error. Because if we take the standard error and instead of saying 1.1 instead of 1.15, right? Well, the difference is 0.05. We have an error of 0.05 doing that. But now when we multiply it by a t-score of 2.3, well, now we've multiplied the error by 2.3. So as you go through these various calculations, it's possible to get a much bigger error than you anticipate because of, how you use the actual data itself. So I'm going to use that actual number. Okay, so 1.31, oops, this tablet is not happy with me here. Okay, 1. Oh yeah, it doesn't want me to use that. It doesn't want me to go back and use my table there. Okay, okay, so now x minus mu is how much? X is 6.7 minus 5 over 1.318. I'm gonna let you get away with rounding to 3 decimal places. Okay, it's 1.5, 1.7 over 1.318. So what's our z-score? What's that? Somebody want to tell me? This is a 1.318 into what is it? 1.29. Okay, that's our z-score, right? Well, now is that far enough apart for me to say that the chances of my getting that result, if these means were the same, if this came from the same population, a population had only gained 5 pounds of weight, not 7.1, can I say that I would get this possible result less than 5% of the time? I can't, right? I can get this more than 5. In other words, I would have to get a result that was almost 2 standard deviations away from 5, either lower or higher, in order to say that my chances of getting such an extreme result in a sample of size 29 would be less than 5% chance, right? So this would be, that would have to be like 2 times 1.7 is 3.4, so this would be 2.6, I guess, and 3.4 on top of that, this would be 8.4, right? So I would have to get a result for those 20, the sample of 29, that's less than 2.6 or greater than 8.4 in order for me to say with 5% chance of being incorrect that these two are different, really different. Well, that's 2 standard deviations apart, below and above. In other words, that this is the percentage of the time that I would get if there's no. In other words, if in fact that this group of 29 uh, 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 randomly sampled steer, if that group of 29 came from a population that had a mean of 5, right? Not 7.6.7, but a mean of 5. I would get a result 2.6 or lower only 2.5% of the time. And I would get a mean of 8.4 or higher only 2.5% of the time. So I would get a mean that's that different, 2 standard deviations different, or really 1.96 standard deviation different, only 5% of the time or less. Okay. So now what percentage of the time would I get a value as high as 1.7, right? Well, that's only 1.29 standard deviations difference, right? So how often would that occur if I had if the real population mean was of this group of steers was really 5, was really 5? How often would I get take a sample and get a mean as high as 6.7? Well, I would get it whatever this area is, right? That's how often I would get a value that high or higher. Okay, so what is that area? Okay, anybody wants to go to the Z table and tell me? What's that 9.9%? I can't get to it because this graphics tablet's taken over my computer. Oh, let me do it. Come on, let me double click it. I'm not sure why it's taken over my computer like this. I think you have it set up differently than I usually do. Maybe because I need to put that down. Under the buttons here. Nope, I give up. Okay, so I'll take your word for it. The Z table tells us that it's how much? Yep, point oh. What's that? 9015. So I'm going to call it 9%, right? Okay, so 9% of the time I would get a value that's that far from my expected mean of 5, right? So now the only problem is that I didn't say what I had said was what's the probability of getting a value that's uh, uh, as different as that amount. When I started this study, I didn't know whether this new feed was going to increase the weight gain or decrease the weight gain. Okay, so in that case, I want to know what's my alternative. That's my hypothesis. What's my alternative hypothesis? Now, normally you do this, but when we go over those 5 steps, normally you would do this step first. But I wanted to show you now that I'm going to go back and then say to myself, okay, my null hypothesis was that it's that even though this came out 6.7, I'm going to start with the assumption that the sample came from a population that had a mean increase in weight of 5 pounds. Okay, so now I'm going to go back and take a look at that again. Okay, I'm going to start with the assumption that the mean increase was 5 pounds, no difference from what I would have expected. But now my alternative hypothesis is that it's different than 5 pounds, that this food made a difference in the weight. I'm not predicting ahead of time whether they gain more weight or less weight. So my alternative hypothesis is that the mean is not equal to 5.0. Right? Well, what does that mean? Not equal to 5.8. That means it could be less or it could be greater. So it just so happened that in this case, the sample came out greater. The sample mean came out greater. But I can't make the assumption that it couldn't have come out lower also. So I have to consider the fact that I could have been that there was a 9% chance of getting a value that's that different than the mean, or there could have been a 9% chance that I could have gotten a value that much less than the mean as well. So my probability of being wrong, had I used this value, 6.7, to reject the null hypothesis and say that this population of steer is different than my original population, then my chances of being wrong was not 9%, but 18%, right? 2 times that p-value. My null hypothesis is on both sides. Okay? Everybody comfortable with that for the moment? You don't have to be totally comfortable yet, right? Okay. Right, twice what the p, because we're doing a two-sided test. In other words, we didn't make the assumption that that our sample mean was going to come out higher or lower than what we expected it to be. Okay. Now, had I said to myself, you know, this sample, this feed that I'm giving these cattle, right, has a lot of protein in it, and it's got a lot of fat in it, and it's got basically nothing else. And I'm taking. It's also got something that will keep the cattle from taking a dump for 2 days, right? So I make some sort of physical assumption that there's no way that the weight gain could have been less than 5 pounds, right? If I make that assumption, I can do a one-sided test instead of a two-sided test. But isn't that kind of a cheat, right? In other words, I'm right off the bat, I'm making the assumption and I know what this food is going to do. Now, it's conceivable that let's say you're a pharmaceutical company and you are testing to see what kind of effect that your drug has on blood pressure. And it happens that your drug is a vasodilator. It's going to dilate blood vessels. You might say to yourself, hey, there's no way they can increase blood pressure. All it can do is diminish, lower blood pressure. Let me do a one-sided test instead of a two-sided test. If I had done a one-sided test here and made the assumption that I can only be greater than 5 pounds weight gain, then I could have used a p-value of not 18%, but only have to worry about one side, 9%. So what did I do? Without changing any of the data, I said to myself, I'm more certain. I think there's less chance I'll be wrong to reject the null hypothesis. It's a little bit of a cheat, isn't it? Which one of these two tests is more rigorous statistically? One-sided or two-sided? Two-sided, because in order for me to reject this null hypothesis, what z-value would I have had to get if I did a two-sided test? I would have to had to get to the point where the z-score was so big that there was only 5% chance or less of getting that outcome if it was from the same population. So how far from the mean would I have to be? 1.9 standard deviations above, 1.96 standard deviations below. So I would have had to have been that far apart or further from the mean in order to reject the null hypothesis. So if I did a one-sided test, I would have been closer to proving that with this sample than if I had done a two. I would have been closer to proving it with a one-sided test, 9% chance of being wrong, than with a two-sided test, 18% chance of being wrong. If I did a one-sided test at that same level of certainty, 5%, I could have tolerated all of that error on one side. And what z-score would have given me a, a value for the probability of getting a value that high or higher? What z-score would have done that for me for 5% at one end of this normal distribution? You already know what it is, right? 1.64, right? It's a 90, remember 90% confidence interval, 5%. So in other words, I would have been able to reject the null hypothesis and say that the mean the mean for the population of steer got this new feed is not equal to 5, it's greater than 5 if I had done a one-sided test. Yes?
So I was reading a study for a paper doing classes where they said that a result was interesting but not statistically significant. So would that be like
this?
We would be this is interesting but not statistically significant?
Exactly right. Now the fact that the magnitude was so much, I mean, they gained 40% more weight, right? Almost 40% more weight. Something like this. What would you do if you thought, gee, I didn't have enough evidence to reject the null hypothesis and say I'm 95% certain, or in other words, I have an alpha of less than 0.05. I think there's less than 5% chance of being wrong, right? I don't have the evidence to say that, but it's still an interesting result. What are some of the things you might do in order to go back and redo this study and give yourself a better chance of being able to have that evidence? Right? You have a larger sample. What does a larger sample do for you? A larger sample gives you a smaller standard error, right? And a smaller standard error means that the difference between the mean that you assumed and the mean of the population you're testing, that can be smaller also and still get you that 1.96 that you need, right? Okay, so yeah, larger sample size might prove that. That might prove that. You never know what you're going to do when you go back and when you go back and do that other sample. Maybe you'll find out that in fact there really wasn't a difference. You just got lucky with that getting that big a difference in the first study.
So here's another question: what about multiple? I mean, I know we're going to get this tomorrow, but what about multiple samples still using NF29? Would that do anything for us?
No, because you're doing the same thing over and over again, aren't you? Right. In other words, what we just seen here is that we would expect to 18% of the time get if the null hypothesis is true, right? And we can't reject it if it turns out to be true, that there is no difference in weight gain or weight loss from this particular diet. We would expect 18% of the time get results in a sample of size 29, this extreme, either lower or higher. In other words, from that population, we get that result, that extreme in this, from this population for that sample size. What we're trying to prove is that it's so unlikely we would get as extreme a value as this in this population, given that sample size, that we can say with 95% certainty that we wouldn't have gotten that sample. We wouldn't have gotten that mean from our sample. Okay, it's a little confusing, right? Let's do this again, except this time we're going to use I'm going to change a few things this time. Yeah.
So when you get a Z-score of 1 point,
I'm sorry. No, I didn't erase that. I'm just trying to. This graphics tablet is confusing me a little bit. Okay, I'm sorry.
of that 0.09, right?
Yes.
So that on the Z table is that it's like 9%. So that's also 6.7.
Well, you're looking at the Z table, right?
Right.
So the Z table, what the Z table is showing you is it's showing you how many standard deviations apart these values are. Like how many Z-score, how many standard deviations apart is the value 5 and the value 6.7, right? And it turns out that it's 1.29 standard deviations apart. So you want to look up a Z-score of 1.29. If you look up a Z-score of 1.29, you'll see that it says 9%, right? So the probability of getting that extreme a value, that different a value, or going that far out on the tail of the normal distribution is 9%. Yes?
So I think on the Z table, the area code is
Yeah, you're reading, it's actually reading, let me guess, it's actually reading 91%.
exactly. So
Right.
Your answer is right.
Yeah, that's reading 91%, but it's reading the area from that point to the left. So that means the area that's above a weight of 6.7 is to the right of that, so it's 9%. In other words, I'll draw that in this. Got it? I'm having a little trouble getting used to this thing. Yeah, let me draw this. I'll draw this now. Okay. We're going to start with an assumption. We're going to start with the null hypothesis that the average weight gain is 5, right? The average, that's our that's our assumption, right? That means that the mean is 5, right? And we're told that the standard deviation is 7.1, right? So that means 50% of the time, if I took a sample of size 29, my standard error turns out to be, what was it again? 1.29. That's my standard error. So what that tells me is if I take a sample of, here's the herd over here. Here's the herd, there's all the cattle. If I take a sample of size 29 from this group, half the time it's going to be less than 5, half the time it's going to be more than 5. Right? Okay. If I take what percentage of the time will it be? I'm gonna simplify this and call this 1.3. What percentage of the time will I expect to get that to have that sample come out to be 3.7? What percentage of the time would I expect to get a value less than 3.7? Right. Well, this is 64, 32% of the time. Right. So in other words, if I told you, I sampled this other herd that was given this different feed, same cattle, same everything, except they were given a different feed, right? And my assumption is that they're really the same mean, right? Sample this other herd, and I got a value of 3.7. Well, I could have easily gotten a value of 3.7 here too, right? That it wouldn't have been that uncommon. It would have come up actually 32% of the time. So it's hard for me to say that these two are not equal, right? Because the chances of my getting a 3.7 is pretty common. So now what if I had said that instead of 3.7, 1 standard error is 1.3, 2.6, let's say that I had said 2.6 would have been 2.6 would be 2.4, right? Let's say I had gotten a value of 2.8. No, I'm sorry, 2.0. Only a 2 pound weight gain, weight gain, right? Well, how often would that have come up here in the original population? Well, if I took if I have this standard error and I took this size sample, right? What percentage of the time would I have gotten a sample where the mean was equal to 2.0? Well, I can calculate that, right? I can calculate the z-score for this value for 2.0 is equal to 2 minus 5 over 1.3 is equal to 3 over 1.3. And that's equal to, I'm going to call it roughly 2.6, 2.3, roughly, right? A z-score of 2.3, right? What area does that leave in here if you got a z-score of 2.3? Pretty small, right? Got it. I'm sorry, no, I'm sorry, negative 2.3, right? Because I'm on the left side. I did that on purpose and then I forgot to mention. I'm sorry? 0.01, 1%. I would get this result from this population 1% of the time, right? In other words, it would be unusual for me to get, if the mean was really 5, it would be unusual for me to get a value as low as 2. That would only happen 1% of the time, right? So what I can say is that that's so rare that I'm going to say that because this came up 2.0 instead of 5.0, the difference is so great that that would only happen 1% of the time. I'm going to say that's good enough for me to say that the real means of these two groups are different. They're not the same. Right? So I just did a one-sided test. If it had been a two-sided test and I wanted to account for the fact that I could have been that far above, which would have been 3 above, would have been 8, right? To account for the fact that, that the weight difference could have been greater by that much also, then that's 1% up there also. So if I do a two-sided test, I always double that area. I double my P, right? So that would be 2%. 2% chance I would get that big a difference. Okay. Why am I doing this? Why am I bothering to do this? Well, the problem is that it's always possible. You know you guys understand the term asymptotic, that something gets close to a value but never really reaches it. This is almost asymptotic. If I really look at this normal distribution, the values, it's entirely possible I could get a weight gain of 0. But how likely would that be? Vanishingly unlikely. Very, very, very super unlikely, right? And I could say, oh, that's really so unlikely it would almost never happen. That would be easy. That would be easy for me to say that there's a difference between these two groups. In order for me to get that small a probability of being wrong, when I say the two groups are different, the two populations are different, I would have to have a big, gigantic what? Sample size. It would have to be an enormous sample size, right? And we generally can't afford to have an enormous sample size. So as an accommodation to this whole, to not having to invest the time and the money in having an enormous sample size, we say to ourselves, we're willing to accept a somewhat higher level of uncertainty than no chance at all, right? So what level of uncertainty are we willing to accept most of the time? 5% chance of being wrong. What does that mean? That means you got 120 chance of being wrong, right? That doesn't sound that good when you put it that way, does it? Right? Okay, however, we're willing to accept that. Well, usually when we're done, we don't get a probability of being wrong of 5%. Usually it's less than that. That's kind of our barrier. That's our mark at which we say we term this a statistically significant result, right? We're perfectly happy, like in what we just did here, to be less than 2% chance of being wrong. We're happier with that. That might even be a more common occurrence. Who knows, right? But we're willing to accept a 5% chance of being wrong. Well, what does that mean? That means somebody's going to come along, maybe try to replicate this study, and 1 out of 20 times, if we actually got exactly 5% chance of being wrong, 1 out of 20 times he might find a different result, even though we were right, even though there really is a difference. Right? So if you use the same sample size, right? Remember, sample size is critical because that determines the standard error and the probability that you have that big a difference. Okay, so we're willing to accept a 5% chance of being wrong. What is that? What is that called? That chance of being wrong? That's our significance. Okay, right? That's our alpha. That's our value. 0.05. 5% chance of being wrong. If I'm doing a study where that's not tolerable, where I'm going to distribute a vaccine that's dangerous or something like that, and I'm saying, gee, or a drug that's dangerous, and I say to myself, I don't want to tolerate only 5% chance of being wrong about the effectiveness of this drug. I could say alpha is 1%, right? 0.01, 1% instead. Okay? So, in a sense, 99% certainty, 1% chance of being wrong, or better, or whatever, or less level of certainty. Or just simply publish and say, we weren't able to prove it to alpha equals 0.05, but, we came close, and maybe somebody also pick up the study with a bigger sample size, or another technique or something like that. Okay, so now